Hello everyone, I hope this webinar finds you well. I see some people are in the process of joining us. Let's give them a little more time. Welcome to Frontline Systems webinar on Analytic Solver Optimization. My name is Dr. Sima Maliki, and it brings me great pleasure to serve as your host. Thank you for joining us. Our plan is to cover a wide range of topics. Due to our time limit, I encourage you to send any questions you may have to consulting@solver.com. This will ensure we can address them thoroughly. Many industries and organizations across the globe for many decades have been using frontline system products for optimization, which contributed significantly to their benefits. Here are just a few typical applications to optimize the use of scarce resources, equipment, facilities, time, money, raw materials, to maximize returns while minimizing risk, to minimize transportation costs and inventory levels, and so on. If you're interested in slides, just email me at consulting@solver.com to receive a copy. Today, we'll focus on mathematical optimization using Analytic Solver. We will start with a multi-step production application in a refinery. We will emphasize how the choice of each formula for your objective and constraints are essential in determining the resulting structure and therefore solving method, quality of solution, and the performance. Then I will show you what you can do within and beyond Excel with an overview of recent and advanced capabilities of Analytic Solver. We will see how we can easily share the model and its results with other users in a repeatable and manageable process using deploy options. After that, we will review a gas industry application with uncertainty and wrap up the webinar with utilizing the power of stochastic optimization capabilities in Analytic Solver to make the best decisions. Analytic Solver is an all-in-one solution in Excel. It completely equips you with optimization, simulation, and data science capabilities. Excel is a powerful tool and easy to start with. Yet to make faster and more accurate decisions, you need to empower yourself with decision intelligence. You need to take the next steps and go beyond Excel and share your resulting insights in a repeatable and manageable process by creating a custom web application or a mobile app. The good news is that Analytic Solver allows you to go beyond Excel with point-and-click deployment of your models. Furthermore, Frontline offers other exceptional platforms such as Solver SDK and Raison Decision Services that equip you with other advanced capabilities. If you want to use programming languages such as C, C++, C#, Java, R, Python, and more, you can use Solver SDK platform. If you're interested to have a web or mobile app, you can use Raison Decision Services platform and REST API. The beauty is that all platforms are fully compatible with Analytic Solver in Excel, and your efforts in creating a proof of concept or a model in Excel are well invested. Now that you are more familiar with an overall picture of our product line, let's open Analytic Solver, beginning with our first example. This is a refinery operations application in oil and gas industry. An oil refinery purchases two crude oils, crude 1 and crude 2. These crude oils are put through 4 processes: distillation, reforming, cracking, and blending to produce petrols and fuels which are sold. How should the operations of the refinery be planned to maximize total profit? Distillation separates each crude oil into fractions known as light naphtha, medium naphtha, and heavy naphtha. Light oil, heavy oil, and residuum, according to their boiling points. A barrel of crude splits into fractions according to this first table. Reforming produces a product known as reformed gasoline with an octane number of 115. The yields of reformed gasoline from distillation process resulting naphthas are given in this table. Cracking is used to maximize the use of oils. The oils, light and heavy, can either be used directly for blending into jet fuel or fuel oil or be put through a process known as catalytic cracking. Next is blending. It is the process of mixing different refinery products to make finished petroleum fuels. Final products contributing to the refinery profit are premium petrol, regular petrol, jet fuel, fuel oil, and lube oil. As we have attendees with varying level of expertise in optimization and model building using Analytic Solver, I'll show how to add decision variables, constraint, and objective function. Then we will discuss advanced modeling topics and explore options for extending our capabilities beyond Excel. What do we need to do to use Solver? We need to determine decision variables, objective, and constraints, and define them using optimization model group. To find out your decision variables, you can ask what factors are under your control. Here, we have control over amount of products to produce in each step. For example, how much crude oil to distill in the first process given certain restrictions. Now let's go back. To define crude 1 and the crude oil to distill as decision variables, select your desired cells. Then go to Analytic Solver ribbon. This is the optimization model group. Go to decisions and normal. You can see under decisions, we also have recourse decisions. We will discuss the recourse decisions in the next examples. So we just use normal for this optimization. As soon as we do this, we can look to the right. This is called task pane. And this is under optimization. We have the objective, variables, constraints, so all the components of your optimization models. These are cells J, 8, and 9, and you can see it's added twice, so let's just get rid of them. I just wanted to demonstrate how you can add a group of the decision variables. The rest of the decision variables are already added in the model. Restrictions on decision variables leads to next component of optimization model, constraints. To determine the constraints, you can ask what restrictions limit our choice of decision variables. For example, the daily availability of crude 1 and 2 are only 20,000 and 30,000 barrels, respectively, limiting the output of the distillation process. So let's add this constraint. Select these two cells. Remember, they are decision variables, but now we want to add the constraint. Here is more like a upper bound, but we still use the constraint, and Analytic Solver automatically recognizes them as the upper bounds. So let's go to normal constraint, less than or equal to, and this is add constraint dialog. So here is the left hand side. You can choose your sign, and then in the right hand side, let's choose K8 and K9. So we are adding two constraints together. Let's click OK. And you can see that Analytic Solver automatically recognizes these are more like a bound on distinct variables, and we have two of them. It's a duplicate. So let me delete one group and erase all drawings. This is how you add decision variables and constraints. All the constraints are added for this model. To determine objective function, ask what measure are we trying to optimize. Here, the objective is to maximize total profit that is calculated in cell C42. We are using sum product, multiplying the outcomes of interest by their respective profit. For example, the profit contribution for regular petrol is 600, for premium is 700. We add all of them together. So we want to define this cell as objective. And to do that, select the cell where you have your formula, go to objective on the ribbon, and here we want to maximize our profit. So let's go to max and then normal. So C42 to be maximized. Now we are ready. Let's go to optimize. You can do solve complete problem, or you can just click on the light bulb. We are going to use guided mode. This is a step-by-step help providing information about the model. So let's click on continue. Few things happen. It analyzes the model structure and is telling us that the model is LP convex. It means all the formulas in the constraints and objective are linear functions of decision variables. So from here, let's click on next step, and here are the results. Solver found a solution. All constraints and optimality conditions are satisfied. Let's click OK, and we get the results. You can view a log of optimization messages in task pane on the Output tab. So you can see that what engine was used and solve time, and this is a message that you can click on, this hyperlink, and it gives you more information what it means. Let's talk about engine tab. If you have noticed, I use Groby in the output, but we can use just the LP quadratic engine. So there are 5 built-in engines for solving different structures of optimization problems. Our model is a linear programming problem, so we can use a standard LP quadratic engine. So let me try again. Click on optimize, and it made escape guidance this time, and here are the results. And now you can see in the output message that we are using LP quadratic engine instead of Groby engine, which is the optional adding engine. Let's go back to engines. So we have LP quadratic GRG nonlinear for solving nonlinear type problems. And then we have evolutionary engines. It uses a variety of methods such as genetic algorithms, taboo search, and it is used for solving non-smooth type problems. Interval global solutions uses interval methods for deterministic global optimization. There are additional solver engines that are commercial products. Groby solver, powerful high performance, Nitro, powerful high performance for smooth nonlinear, and much more. Now, I want to show you how adding a new constraint can change the structure of your optimization model. Let's look at the result. There is no regular petrol produced to maximize profit, basically because premium petrol was contributing more to our profit. So in the optimal solution, we're only producing premium petrol. Imagine you want to express a relationship that seems to require dividing one or more variables by other variables, or you want to calculate and limit the weighted average of variable. We call this ratio constraint. Let me show you the shape of ratio constraints. So dividing one variable by another, percentage constraints, and weighted average. And in our example, let me show you the ratio. Okay. We want to add this constraint. I put it in this box. Let's assume we have to ensure regular petrol produced must be greater than or equal to 25% of our total petrol produced. I have this constraint right here. So D36 divided by D36 plus E36, and we want to make sure this is greater than 25%. This is cell H41. I've already added the constraint H41 greater than 25%. Now, let's go ahead, click on optimize. What are the results? Click on continue. As you can see, our model is diagnosed as nonlinear programming, non-convex, or just nonlinear programming. If you add these constraints in this way, The constraint left-hand side is a nonlinear function of the variables, so the model structure will change and it will not be linear anymore. As you can see, the model is nonlinear, non-convex. Now, let's click on next step, and we get the optimal solution. And we are meeting the requirement. This is a small model. In a large-scale application, this might cost us time and a suboptimal result, meaning just a feasible solution. There is a simple resolution for this. To resolve this, we can choose a different approach. With some reformulation, you can keep your model linear. Let's go back to slides. I want to show you the math, and then we come back and apply to the model. Here I show you the steps. Multiply both sides by the denominator, collect the like terms, and do the math according to the signs, and now you have a linear function. This transformation assumes the denominator is not zero. This is a linear transformation for other similar ratio constraints. So this is what we want to do for our example. Let's go back to our model. I have another version of the model. I'll show you how you can do the math in this section. So we need to add this constraint, okay? And I have this constraint in cell G41. 75% of D36 minus E36 should be greater than or equal to 0. So I've added this constraint. Just go to constraint, normal constraints greater than or equal to, and then here add 0, click OK. And you can see that we have a duplicate of ratio constraint. I just gave it the name range, ratio constraint. So let's delete one of them. Now let's click on optimize on the ribbon, click on continue. Two things happen here. Analytic Solver analyzes our model and finds out that the model structure is LP convex. Great, so we are back to having a linear model. My engine selection was GRG nonlinear. This is not recommended and is giving me choices on the other engine that can solve a linear convex type problem. So let's choose the standard LP quadratic and click on next step. And here are the optimal results. As we just saw, the mathematical methods needed to solve your optimization problem depends on the relationships defined by your formulas between the output cells, objective and constraints, and the input cells, decision variables. So we have three solving methods. The simplest LP method assumes that the formulas that calculate your objective and constraints are all linear functions of the decision variables. When this is true, solver can quickly find the globally optimal or very best feasible solution for you. The GRG nonlinear method assumes that the formulas that calculate your objective and constraints are all smooth linear or nonlinear functions of the decision variables. When this is true, solver must do the work, taking more time, but it can normally find the locally optimal solution, the best feasible solution in the region around the starting point. The evolutionary method makes no assumptions about the formulas that calculate your objective and constraints as functions of decision variables. When this method is used, solver may take much more time and it can only find a good solution improved from the starting point, not an optimal solution. And you know when this happens? A lot of time using if, VLOOKUP, and other non-smooth functions in Excel, where the conditional part depends on your decision variables, will cause your models to be non-smooth, and then you have to use evolutionary methods. And there are workarounds and there are ways to linearize your model. So if you're interested, this is something you are dealing with right now, email me and I will send you the set of slides with all the tricks and hints for linearizing different functions. Today we saw that adding a ratio constraint could totally change the structure of your model, but we could easily linearize that ratio constraint. Good news is that Analytic Solver determines for sure whether your model meets the assumptions, so it can automatically select the best solving method or engine from more than a dozen choices. Remember to use guided mode to get more detailed information about your model. And we also saw that how using guided mode prevents us from making an error in choosing the right engine. Let's go back to Analytic Solver ribbon. Regarding optimization, using Analytic Solver, you can also access multidimensional modeling. It's a very helpful tool when you're building large-scale models where there are multiple products, projects, or investments, or time periods, or multiple sources and destinations, and it turns a very complex, hard-to-maintain spreadsheet problem into a simple, well-structured, easily maintained, and expandable model. Then you have the simulation model group. We will use simulation model group along with optimization when we want to define the source of uncertainty. We have decision model group, and under parameters, you can define multiple parameterized optimizations. And you can go to AI agent. Our Analytic Solver AI technical support agent is based on the same technology as ChatGPT. It has studied thousands of pages of frontlines, help, and user guides, everything about optimization, Monte Carlo simulation, data science, and machine learning, and much more is available for you to utilize. If you're interested to learn more, click on Help. You can click on User Guides to access Analytic Solver User Guide and Reference Guide. I highly recommend using Analytic Solver User Guides chapters on advanced topics in optimization that you might find very helpful. You have access to example models. Their optimization, you can find examples in different industries. You can go to education and training. If you're interested, you can go to Solver Academy and learn about different courses on optimization, simulation, and data science. Okay, I have a different version of the same problem, just one workbook, original model that we looked at. So let's bring that one. Let's go to Analytic Solver ribbon and click on Deploy Model. We use Analytic Solver to create and solve an optimization model and get results. Now let's take the next step and find out how to share our model and its results with others in a repeatable and manageable process. Of course, you have shared spreadsheets. However, we offer you a very powerful capability that is unique and leverages your spreadsheet modeling strengths and takes it to a whole different level. Let's find out how to enable your models to be used whenever and wherever it is needed. You can achieve this by using a cloud service, which is made available to you by Frontline Systems, and it's called Raison Decision Services. You can deploy your analytic models to the cloud to Raison server, which is a REST API, entirely within Excel, as we will see, and even check runs of your models without leaving Excel, so no code. With the deploy options, you can turn your Excel model into a cloud service in seconds. This is only one way. We have created multiple examples to demonstrate these limitless possibilities. You can easily host your optimization model results in Microsoft Teams or embed your models into your own application and solve it on the web or within Power BI or Tableau by calling a Raison server. All these options allow you to make results conveniently available to others. We are going to explore a few of these options. The first one is Teams. If you want to share your interactive model results without sending the whole workbook, you can send the report through Microsoft Teams containing interactive links to your original workbook. And you can choose exactly which part of results to include in that workbook. Let's go step by step. Your workbook must be saved in a location that is network accessible, such as OneDrive or SharePoint. Mine is located on Frontline Systems Business OneDrive, and you can see that my autosave is on. Step 2, You must first solve the model and save the workbook. Otherwise, Teams would not be accessible, which makes sense because you want to share the results. And here you can see that Teams is grayed out. So let's close this, solve the optimization model first, continue, and here are the results. Now let's go to deploy model, Teams. You can see it is available. Click on Teams report. And now we have the first dialog where you can select the model components to include in the Teams report. You can choose one by one what you want to share, or just click on this button to include everything and then click OK. Now you can select the team and channel where you would like to share the results. You can change your workbook name. So I'm going to choose test team and use general. You can change your workbook name here, and you should type a quick message for your colleague. Hi, here are the latest results. You could also choose report options, report name and date, other details, and click on send. In a few seconds, a message will appear. Here is the message reporting that the report was sent successfully. As soon as you click OK, Analytic Solver will automatically create a new workbook holding only model results with external links to your model workbook. This new workbook will be saved online and made available to users you want through a Teams channel that you select. And you can see that the optimization Teams report is inserted to the left of our tab. Now let's go to Teams. And let's go to Teams where you have the results. So large, okay. Under General, this is what we created. You go to Teams, proper channel to find the report. You can click on the report to open it. You want to make sure to enable the content and trust workbook links. And here are the results. So remember to click on enable content to enable the content on the report and trust the links. Now your colleagues can see your model results in Microsoft Teams. If you go back to Teams, you can see that you could open this report in Microsoft Teams, desktop Excel, or the browser. Now, if a parameter changes in the original model worksheet, simply resolve the optimization model and then click the refresh icon on the workbook links pane. There is no need to deploy a new Teams report. This is just an example of what can be done. You are invited to customize this report in the design of your choice. To save time, I'm going to skip Power BI and Tableau examples. There is a recorded webinar at our YouTube channel that you can view at your own pace, and you can find it under YouTube Frontline Solvers. Go to Educational Webinars, and here's the webinar. How to share your model and collaborate in Teams, Tableau, and Power BI using Analytic Solver. And also, I highly recommend you to watch this recording, The Art of Designing Models to Get the Best Answers. It talks more about the structure of your optimization model and also how to linearize like if functions and some more of non-smooth transformation. Okay, let's go back to Excel. Let's click on deploy model. If you're not sure which of the deploy options to choose, you can use deployment wizard to help guide you through the deploy menu options. Click on next, and you will be guided to select the best way to deploy your converted Excel model. Okay, let's go back to deploy and let's practice another option. Let's go to cloud service and let's use Excel model. This option makes things very simple. Select Excel model. Let's give it a name, new binary operation optimization. I'm going to delete the extra, and you can have your workbook on OneDrive and click on save. This saves our model to the Azure cloud, and it saves a copy of your workbook in your account on public Rayson Cloud service. As soon as I click Save, it posts the Excel workbook to Rayson server, and immediately you saw that Rayson.com opens and displays the model without translating the model into any language like Rayson language. With this action, our Excel model itself is now promoted to Rayson server as a cloud service. Here you have different options on Rayson.com. This is the editor page of Rayson.com or Web IDE. You're looking at Rayson server through a front-end portal, which is at Rayson.com. So in the background here, there's a REST API service that can be used by any application. And to make it clearer, Rayson.com itself is also an application that uses the backend service at Rayson.net, which exposes a REST API and allows any other application to perform optimization, simulation, invoke a trained model, and much more. Let's go ahead and solve this optimization model. We submit any model to the queue, and results will be available in two formats, JSON and OData. Here are the results in OData format. And if you're interested to see the results in JSON, just click on this button. So you can switch between JSON and OData. Okay, let's go back to Excel. You can just click on Deploy Model, Create Cloud Service, but you can translate the whole Excel model to Rayson language and then post it to the server. So that's okay. Let's click on Save. This time, the whole model will be translated to JSON language. Here it is, and then you can solve it and get the results. So you can create a cloud service from an Excel model itself, or you can translate it to Rayson language. Now, let's go ahead and try one more thing. Let's go to Quick Test and create a web page. Immediately, Analytic Solver translates the Excel model into Rayson language. Here it is. And a browser opens, displaying the newly created web application. It creates a web page, and you can see it's an HTML web page that uses simple JavaScript. And here we are calling our Rayson REST server at this URL. This is your unique authorization token, and you can have data files. You can choose your model here also because this is a template. To view the source code used in this web application, right-click and click on View Page Source. And a browser opens, displays the code for the web application. As you can see, we use HTML to define edit fields and buttons, and we use JavaScript to run the flow by making REST API calls to the Rayson server. This is a working version of your model that runs on the web. And if we go back, we can go ahead and solve the model. So we have options to click on Solve or Quick Solve. And the model is submitted during this time to Rayson server, and optimization is started. And here are the results. Same solutions that you would see in Excel, but here they're returned in JSON or JavaScript object notation. We created a web application from a model that was initially in Excel, and we did this with a few clicks. This ability in Analytic Solver bypasses months of development work for you. This template for this HTML page is shipped with our software, and it sits in your example folder. There's a file called Rayson template. You can double click on it and it opens in a browser. You can edit it with Notepad. By using Rayson Create App web page, we learned an easy way to share our results whenever and wherever needed. We learned to communicate with Rayson REST API beyond Analytic Solver and Rayson from a web application. Now we can stop the deployment options and focus on stochastic optimization. So let me close this workbook and also this one. Let's have a brief introduction into stochastic optimization components, then return to an example to practice it. The key concept is that a certain parameter has a single known value. However, an uncertain parameter has many possible values. We call each such value a realization of the uncertainty. In this slide, I have pictured one certain and three uncertain parameters. We will divide uncertainty into two general situations. In some real-world problems, we are certain about the value of a parameter today, and we will remain uncertain about its value in the future, and we have to make decisions in the presence of this uncertainty. In other real-world problems, we are uncertain about the value of parameter today, but we will know its value with certainty at some point in the future. A good example is a marketing or finance model, where a competitor's price or next year's commodity prices or interest rates are uncertain today, but will become known at some future date. We say that the uncertainty will be resolved at the future date, and at that date, its many possible values will be reduced to a single value, and the uncertain parameter will become certain. If we are dealing with uncertainty that will not be resolved, we must find values of decision variables that yield feasible or nearly feasible solutions for many possible realizations of uncertainty. On the other hand, if we are dealing with uncertainty that will be resolved at a future date, you can ask, what are the decisions that you must make here and now before the uncertainty becomes known, and what are the decisions that you can make on a wait-and-see basis after the uncertainty is known. We call the decision variables that we must make here and now normal or first stage variables, and we call the decisions that you can make on a wait-and-see basis after the uncertainty is known recourse or second stage variables. At the time the optimization is performed, a single recourse variable effectively represents an array of solution values, one for each realization of the uncertainty in the model. Here is how we classify stochastic optimization problems. There are three solution methods currently supported by Analytic Solver: robust optimization, stochastic programming, and simulation optimization that can be applied to these problems. If a constraint depends on uncertain variables and normal decision variables, we must specify what it means for the constraint to be satisfied. For example, we might specify that the constraint must be satisfied 95% or 99% of the time, and it can be violated 5% or 1% of the time. This is one form of a chance constraint. It must be satisfied for all realizations of the uncertainties up to a given percentile. A var constraint with probability of 95% requires only that the constraint be satisfied, not violated 95% of the time. In contrast, conditional value at risk measure specifies that the expected value of all the realizations of A1 up to the 95th percentile must be less than or equal to B1. Let's look at our next example with two approaches. First, with gas company chance, you will see how a problem with uncertainty can be formulated with a chance constraint and solved using robust optimization methods. Then with gas company recourse, you will see how to use a wait-and-see or recourse decision to obtain a better optimal solution. In this model, a gas company purchases natural gas from suppliers and resells it to consumers in its service area. Consumer demand is known to be 100 units this year in cell D22. But it is uncertain for next year. The company must meet this demand with high probability or it will encounter regulatory problems. The price of gas known to be $5 per unit this year, but it is uncertain for next year. If the weather is very cold, demand may reach 180 units and price may reach 7.5 units. But if the weather is warm, demand may remain at 100 units and the price may remain at $5 per unit. A beta distribution is used to model the weather. The company goal is to minimize its total cost of purchase and stored gas. Our decision variables are how much gas to purchase and resell to consumers this year at cell E29, how much gas to purchase this year and store at a cost of $1 per unit for use next year, and how much to purchase and resell to consumers next year. We assume that gas company must commit to all of its gas purchases this year before the next year demand is known. Therefore, all of our decision variables are normal or here and now decisions. Now, the constraint is that the company must have enough gas to meet next year's uncertain demand with high probability. This is modeled with a chance constraint. This is our chance constraint. var d38 greater than equal to 0 should be with a chance of 95%. So you have to go to constraint, chance constraint to define the chance constraint. Now let's look into objective function. Our objective function is total cost to be minimized, and it depends in part on next year's uncertainties of gas price. Therefore, we have to minimize the expected value of total cost. So to do that, you can select a cell, go to objective, go to minimize, and use expected. So at D37, we calculate this year's gas purchase minus this year's demand, and D38, we calculate gas purchase and store this year plus gas purchase next year minus next year's uncertain demand, and these two have to be greater than or equal to 0. There is a normal constraint D37 equals to 0 that specifies that we must meet this year's consumer demand exactly, and this forces E29 to be 100. Let's go ahead and click on optimize and see what Analytic Solver does about this model. Let's click on continue. Analytic Solver can automatically transform this stochastic linear programming problem with its expected value objective and chance constraints into a larger conventional optimization model using the methods of robust optimization. Let's click on next. So it is telling us that we transform the model with uncertainty into its stochastic programming deterministic equivalent. Let's click on next, and we get the results. So Solver found a solution for this problem. You can click on this message to display help with more complete explanation of what this message means. And if you want to resolve the formula in D41, you can just click on simulate, run once to run a simulation, and you can get the expected value of the objective, which is about $1,446. You can click on reports and get an answer report, and you can see that we meet our consumer demand about 95.7% of the time. Let's go back here. I want to show you something else. I want to show you the difference between the original model and the robust counterpart model that's a result of the transformation. So you can see the structure differences. Let's go to this button, Analyze Original Model. This model is diagnosed as stochastic LP with 3 variables, 3 functions, and 1 uncertainty. And let's go to Analyze Transform Model. Continue. Next step, and you can see that the transform model is LP convex, and it has 9 variables, 8 functions, and it has 0 uncertainties. Just wanted to show you the difference between the original model and the robust counterpart. This is a very simple model that could have been solved via simulation optimization, But with robust optimization, we can scale up a model like this to a large size and solve it efficiently with LP quadratic solver or any of several large-scale solver engines. There is much more to discuss here, including auto-adjusting chance constraint, and all of these are discussed in this webinar. So if you go to our YouTube channel, there is a recording on make best decisions under conditions of risk and uncertainty, and you can learn more about the concept of chance constraint and how to get the solutions the way you want. Now, let's look at an example with a different approach. Let's go to gas company recourse. So we have a solution to the gas company problem, which was found with robust optimization, but we can do better than that, and we can reduce our expected total cost to around 1,200 and a little bit more. A significant improvement. Let me show you how. We can do this provided that the business situation permits us to make decisions of how much gas to purchase next year on a wait-and-see basis after the uncertainty of the weather is resolved, a so-called recourse decision that was discussed in the beginning. Here, the gas supplier must accept our purchase order next year and not require us to commit to a specific amount of gas this year for delivery next year. If the business situation permits you to make some decisions on a wait-and-see basis, it is crucial to include this in your optimization model. If you don't do this, you may find an optimal solution to the wrong model for the actual business problem, which we have seen happens for many people, usually for two reasons. Either they are not familiar with this concept, or the software doesn't allow them to create models with recourse decisions. While simulation optimization is very popular, it has no concept of recourse decisions. Analytic Solver is very unique in offering this capability. So, in this example, gas company recourse, we assume that our decision of how much gas to purchase next year can be made on a wait-and-see basis after the uncertainty of the weather has been resolved. This model has the same objective, so let's take a look. Expected value of T40. E29 and E30 are the same as previous model, but E33 is different. This is the amount of gas to purchase next year, and it appears under recourse. So we have two normal variables and one recourse variable. And remember, to define a variable as recourse, you just select the cell, go to decisions, and choose recourse. And D38 is no longer a chance constraint. It is a normal constraint, and it is in equality form. We expect to satisfy next year consumer demand exactly. So we have D37 and D38 equal to 0. The recourse decision variable allows us to do this. In each possible future scenario, once the weather uncertainty is resolved and the consumer demand is known, we will purchase just the amount of gas we need to meet demand. We cannot solve gas company recourse with simulation optimization because it doesn't have any concept of recourse decisions. But we can use robust optimization methods to transform and solve gas company recourse, much as we did with gas company chance. And you will see that our recourse decision variable will have many possible values at the optimal solution, one for each realization of the uncertain demand. Let's go ahead and click on Optimize. Click on Continue. Analytic Solver tells us that model was transformed into a stochastic program in the deterministic equivalent, and click on Next Step, and finds us the optimal solution. Here are the results. Normal variables have the optimized value, but I want to show you that the single recourse variable represents an array of solution values, one for each realization of the uncertainties in the model. So to see these values, I'm going to cycle through some of the trials, and you can see the values on the model changes. Pay attention to E33. As you can see, E2930 has the optimal values, but E33 has all the realizations of uncertainty. Same with the objective in this cell. Here is the expected value of the objective, which is about 1,284, and it's a considerable improvement over the minimum cost of about 1,446 in the gas company chance. And you can double click here and see a histogram displaying all 1,000 trial values for our objective with all the related statistics, percentiles, Six Sigma, and much more. If you want, as I showed you, you can double click on the recourse decision variable and see histogram displaying all of 1,000 trial values for this recourse variable, along with this some related statistics. Our optimal solution is to not store any gas in year 1 for use in year 2, but instead to buy just enough gas to meet the uncertain demand in year 2. Now, assume time passes, say 6 months later, and the uncertainty has become known. Basically, the gas price in year 2 is known, and hence demand in year 2 is known. Then you or just the user of the model can replace uncertain variables with those known numbers and do a simple solve, this time solve for recourse variables in the software. And there is an option for this under Optimize. Solve for recourse variables. So let's do that. Let's replace the uncertainties in the model, and you can just remove the beta distribution and replace it with a fixed value. And remember, we are not going to change the stage 1 variables because they were dealt with 6 months ago. And we don't have any uncertainty anymore. We just have to find out the optimal value for the recourse variable, which is now become a regular decision variable. To replace uncertain distributions, there's another way to do that. Just double click to open it. You can replace it with a constant, or you can use a cell lock to fix it without destroying the distribution. So there is a control parameter called lock, and let's lock this distribution at a value of 0.4 and click on save. Now let's go to the optimize, solve for recourse variables, and we get the optimal results. So the optimal value is 122 for gas to buy and resell in year 2. This was just an introduction to Analytic Solver stochastic optimization capabilities. There is much more for you to explore, and feel free to attend Solver Academy courses or refer to User Guide Advanced topic or watch the YouTube video that I showed you. Okay, let's go back to our slides for a recap. Excel makes it easier to start with analytics, build your first model, show the proof of concept. Analytic Solver runs on Excel for Windows, Excel for Mac, and Excel for the web. Today, we explored a few of Analytic Solver's capabilities that are available to you. We learned that Analytic Solver has the full spectrum of capabilities for analyzing and solving optimization models that must allocate scarce resources in the presence of risk and uncertainty. Analytic Solver offers state-of-the-art technology on stochastic programming and robust optimization methods. It has the fastest performance in simulation optimization, many times faster than its competitors. Furthermore, Analytic Solver delivers the unique capability to define and solve problems with wait-and-see or recourse decisions. Without the right tools, your resource allocation problems under risk and uncertainty can become difficult and expensive to solve. Now you're aware that the capabilities of solving large-scale optimization problems with uncertainty in Excel and beyond is already yours. Furthermore, you deserve to experience an unparalleled freedom beyond Excel. We saw today that you can effortlessly deploy your models to the cloud, craft custom applications, and explore new possibilities. Today, you got familiar with Analytic Solver and Raison Decision Services, two of Frontline Systems products. With Analytic Solver plus Raison, you can promote your models to run them on Raison Cloud Service and make the results easily available to other people. We invite you to begin exploring Analytic Solver and Raison decision services. Here is my contact information along with that of our other team members. You are welcome to contact us with any questions or comments. I enjoyed presenting this webinar to you and trust that it was helpful. To learn more about other features of Analytic Solver, feel free to join us in the upcoming simulation and data science webinars. It is time to end this presentation. We appreciate your time and interest and look forward to hearing from you. Bye for now.